All right, what we do, we spend a few minutes making some comments to what I sent you as a proposal to make an exercise using a piece of code that is shown here. Now we are using the piece of code in MATLAB, and the example is the dual example of what Julia showed you. So Julia showed you that it's possible to build the appearance of a propagative function that is sliding, so that the cable can show a propagative shape that is sliding from one side to the other side. And she showed you how this propagative shape is built, making the superposition of the standing wave solutions associated to the initial condition given in terms of position. So she made the example of the propagative of the standing wave solution with an initial condition with given position 0 velocities. All right, and she showed you how to build this this free motion solution of the problem as the superposition of the infinity Fourier series representation of the standing wave solutions. All right, so building, summing up all of those, you are building a propagative and what has an appearance of propagative solution, and this is given in a MATLAB code that she gave you. What we do now is the dual is what we should have done at the very first day. So to show that in case we are using as a propagative solution of the problem, the propagative solution, a shape that is actually a sinusoidal shape, for example, going from one constraint. So this is one constraint, this is the other constraint. We have a cable that is running from 0 to L. So the real cable is this one that is shown here. This real cable is tensioned, okay? Is tensioned. And now what we do, we make the exercise of taking a shape that you recognize, that is the shape of the second mode of vibration of the cable. And we build two of those, just in order to make that the total has the amplitude equal to 1. We put amplitude equal to 1/2, but it doesn't matter. So they must have the same amplitude. This is a sinusoidal wave that is having a wavelength equal to L. So lambda2 is equal to L. So the wavelength is the length of the full wave, the positive and the negative part of the wave. All right. And so we make so that this is sliding with the velocity c into the positive, into the progressive the direction of the propagative solution. In order to make that, we are just putting into the solution not just x, but x minus t. So the same function, the same function where we are substituting instead of x, the quantity x minus t is becoming the propagative function, the same propagative function that is sliding into the positive direction with a velocity c. All right? And then we make exactly the same, but substituting into the f2 instead of x, x plus ct. And so we are making the regressive propagative version of this wave. All right? And so we are building the two waves that are sliding, one in the opposite direction of the other. It is possible, and into the slides that you have, there are the calculation to show that if we are developing this object through the Prost-Afferesis formula of the trigonometry, it's possible to separate. So it is possible to build this function in terms of sinus alpha più beta, that is equal to sinus alpha cosinus beta plus cosinus alpha sinus beta, okay? So using the formula, the Prostaphèresis formula, it is possible to open all of that and to make so that, given that here it is plus and here it is minus, some terms are cancelling, and what is left is actually the shape, the same shape that is moved by a time domain harmonic function that is giving the version of this problem in terms of standing wave. So we are understanding from an analytical point of view that adding up two objects like that, the two waves that are sliding one in the opposite direction of the other with the velocity c, what we are building the same standing wave that is oscillating harmonically, and this is the point. It is oscillating harmonically with a very specific frequency. So the frequency is higher intuitively. If the speed is larger, the frequency is higher, isn't it? So it is obvious. Obviously, if the phenomenon is very quick because they are sliding very quickly each other, the frequency is higher. And so the frequency is depending on the velocity of propagation with which we are making the two harmonics sliding each other. So what we do now, I'm sharing the screen, and didn't work. It didn't work. All right. So what we see, the red, if I'm not wrong, is the regressive. The blue is the progressive. And what we are doing, if you look at that carefully, you see that the blue is going into the progressive direction, the red is going to the regressive direction. But what is the secret is that doing that, so making the same velocity that is going one side to the other, what is happening is that the positive and the negative here at the constraint, they are adding up. And so what is happening is that making the two shapes, sinusoidal shapes, sliding at the same velocity, given that the shape is exactly the same, the constraint, the constraint request is always verified. And so the two shapes that are sliding in the opposite side, one with respect of the other, because of what is getting down here is getting up in the other one. And so the constraint is continuously always satisfied. And what is very curious is that because of the properties of the sinusoidal shape, 1 second, that this has stopped. So when they are superimposed, they are just adding each other. But if you look at what is happening in a position like that, when in a situation like that, you see that they moved 1/2 of the wavelength. The red one moved 1/2 of the wavelength in the negative direction. The blue moved 1/2. They moved 1/4 of the wavelength in the regressive direction, the red. 1/4 of the wavelength in the progressive direction, the blue. And what is happening is that because of the symmetry, the addition of the two is making the null, the straight line, all right? And then what is looks like to be like a miracle is that moving each other, what is happening to the total is that the total is just the original wavelength that is modulated. That is modulated by a time domain function that is moving from an amplitude that is 1 to an amplitude that is null to an amplitude that is -1. And so the reason for doing that is making so that you are working, you are putting your hands into the code, and you are making it work, and you make some minor modifications. So the minor modification is to understand, to look at with your hands that if we are making this quantity, we are writing down here lambda 2, where this lambda 2 is the length 0L, when you recognized, because you did with Julia last time, that the fundamental wavelength of the cable, the first mode of vibration of the cable that is simply connected to constraints from 0 to L is the lowest frequency mode that is oscillating in that way, but the wavelength of that is not L, is 2L, all right? Because it's clear. So this is the full wavelength is this one, all right? So the wavelength of this shape, sinusoidal shape, is 2L. And so if we are saying, if you are looking at the representation of the different harmonic functions that are consequent of the infinity way of movement of the tensioned cable, we are recognizing that the wavelength of the subsequent shapes are just the lambda 1, where is it? Are just the lambda 1 divided by n. So the nth mode having a frequency that is n times larger than the first has a wavelength that is 1 divided by n, but where lambda 1 is not L, is 2L. And so in purpose, in order to use something that is clearly is showing its own wavelength, I made the exercise using the second mode. The second mode having a wavelength that is very clear, that is L, all right? And so the request is that you are playing, you are substituting, you are changing a bit the piece of code, making also the other wavelengths, all right? And what is interesting here is that there is no information about which is the frequency. We are making this exercise. We are just sliding the two shapes one towards each other with a velocity. We are giving the velocity, all right? And we do not have the information about which is the frequency that is getting out of that, all right? And so my suggestion is to find a way to, looking at what is happening here, to calculate, to understand, to looking into the code, to find out when it happened that one period of oscillation has passed. Okay? So what does it mean? It means that we are starting with the condition of the cable that has the full the configuration like that. Then it is going down to have a null amplitude. It is going down to have a negative. It goes up again to the position where it did come from. All right. The time that is passed from the starting condition to the second condition when the shape is exactly the same, this is the period of the oscillation, and the frequency is 1/2. So the frequency is the reverse of this period, 1 divided by this period, all right? But it is at the same time absolutely clear, try to think about that this period must be equal to the time that is taken by the original wavelength to move from here to there. All right? Because when this wave moved from here to here, it is equal. It is totally equal. But we have to wait that the full length of the wavelength has passed in order to have the new wave to show up exactly the same. So all of that is becoming a little bit more tricky in case instead of having one single wave, we have several waves into here. If we have several waves, the time that is taken in order that everything is repeating exactly the same is not the time that the wavelength is coming from here to the constraint. It's just the time that is taken for, I cancel the drawing. This is the constraint, this is the other constraint. If we are considering this one, all right. And we are building the same problem with, this is what? This is the fourth harmonic, because it is 1/4. So it is the total length, the wavelength of the first is 2L, and the wavelength of this one is 1/2 L. And so this is the fourth harmonic. So in case I slide of a length that is lambda 4, everything is equal. So I am repeating exactly with the shape that is like that, and everything is exactly the same. And so the time that is taken in order that everything is repeating equally, it is the time that this L4 takes in order to move with the velocity c from over the length. And so the idea that we must have, I suggest that you can use this way of thinking, different way of thinking, so everyone can do what he wants. But what should be left from this insight is that the period is equal to the wavelength of the specific harmonic that we are looking at, divided by the propagative velocity. And the frequency is equal to the velocity of propagation divided by the wavelength of the harmonic that we are looking at. And so then I will write Fn equal C divided lambda n, and Tn equal lambda n divided by C. And so we must have in mind that there is those consequences. So if we have the propagation velocity, we have the wavelength, so we have the frequency and the period of propagation, all right? And the other thing that we have to bring to get from this example is that the propagative solution and the standing wave solution are exactly the same, but the mathematics is a little bit different. They are saying exactly the same things in a different way, all right? And it is possible, absolutely. So you first, the last time with Julia, you did the exercise of showing a propagative example that is coming from standing waves to superimpose each other. And here we are showing very specific, of course, a very specific propagative initial shape that is transforming into the fundamental standing wave that we are using into the examples. So the mathematics is a little bit different, but we can show the same things with the two approaches. Of course, who is the winner? The standing wave. The winner is the standing wave because it is extremely simple to use, extremely general, and then it is intrinsically, it is showing something that is showing the shape of the modes of vibration and the time domain function that is modulating it, that is very, very consistent in a physical way of recognizing what is happening in our experience. All right. Then tell me if there is something left. Of course. Together with those slides, I gave you those pages that are the pages of the book which are collected the characteristic of the cables. You are engineers and you must be very interested in those numbers. So what does it mean? It means that we are asking you those numbers. So if you are not interested, you must be very interested, all right? And so we are requesting you to spend some time looking into those way of making the calculation. That is maybe a bit different from the way that we do analytically. So it is very interesting, in my opinion. And so to become very familiar with those numbers. And for example, we are using as an example a cable having a diameter of 50 millimeters, making the calculation that there is an effective area that is less than the nominal area, that is just the circle. It is less because there are some voids, some empty spaces. And so we are calculating the mass per unit length, paying attention to the effective area. And if you are calculating the propagative velocity, we are dividing the tension in the cable divided by the mass per unit length, but the tension is the effective area multiplying the maximum sigma that is multiplied by the load factor with which we are using. And so with those numbers, given the diameter, the effective area, the mass per unit length, and the propagative velocity that we said, it is 200 meters per second. All right, which is the tension? It is obvious. Which is the tension? It is obvious. So we are calculating from this formula, which is the tension, given that this is the material. All right, and so we know which is the tension that is going on into this cable. And so please be aware of what you're doing, which are the quantities that you're using. Be aware that the propagative velocity is this quantity here. The sigma of the material multiplied by the load factor with which you are using the material divided by the density of the steel, all right? And so if it is increasing just because it's increasing the maximum sigma and just because we are going up with the load factor, all right? But the maximum load factor is 1 when we are breaking the steel because it is too loaded. And so this load factor, we are here, it is a very, depends, if it is 2000, this quantity, we get that the load factor with these numbers is 15%, 20. All right, we stop here. All right. Well, stop sharing. All right, so 1 second that we go to the other point. Okay. So what we do today is an example . what I have to, so this is a cable that is made by we have two domains, larger, so a larger diameter cable, a smaller diameter cable, so a larger mass per unit length here, a lower mass per unit length here. What I have to, here this M1 is larger than M2, T1 is larger than T2. No, is equal, all right. T1 is equal because the two cables are absolutely sharing the same tension that is running, that is tensioning the two cables altogether, all right? Is it clear? So we are tensioning the system. The two cables are sharing exactly the same tension, all right? And so the propagation velocity is C. Propagation velocity, C, tension divided by mass per unit length, all right? So where is larger the mass is lower the velocity. And so C1 is lower than C2. The propagation velocity where it is heavier is larger. So we go ahead showing that F1 so we understood from the previous example that we can say that the frequency is the propagation velocity divided by the wavelength. Okay, whatever is. And so we have one cable, the first cable, that has propagation velocity C1 and wavelength lambda 1 that is unknown. But we know, here we are showing the frequency. So we must be convinced that if this object is oscillating, it will have a first mode. It will have a first mode of oscillation that will not be like that. It will not be like that. It will be different. It will have a different shape, all right? In this different shape, it will happen that there is one first thing that we must be aware of. The frequency is the same on the left and on the right because we have one mode of vibration. The structure is made by by pieces having different characteristics, but the frequency of the overall mode of vibration of the structure is exactly the same. So we are not speaking about the frequency of the left side and the frequency of the right side. The period of the oscillation will be the same, all right? In the connection among the two cables are moving exactly in the same way, and they have exactly the same frequency, all right? And so we must write that F1 is equal to F2. And so they must be equal. The ratio of the two must be equal. And so where we have the larger mass, we have the lower velocity of propagation, and this must be intuitive. So if you have more inertia, the velocity of propagation is lower because the vibrations are always made by a competition among the stiffness and the inertia. The stiffness is given by the tension. The inertia is given by the mass. The two objects are sharing exactly the same tension, so they are sharing the same stiffness, but the mass is larger here and the frequency is lower. So we must have this intuitive vision into the vibration. And so the propagation, I said the frequency, I wanted to say the propagation velocity. So the propagation velocity in 1 is smaller than in 2, so that the wavelength in 1 is smaller than in 2, because the ratio must be the same. And so if I have to show which is expected to be the deformed shape of the first mode of this object, I have to show that I have somehow a wavelength into here that is smaller than here. And so I have to make somehow maybe a drawing that is going like that. All right? So here is the connection. So what I want to say is that here I recognize something that is a wavelength, a wave, the shape of the wave that is interesting the larger mass object. And here is the shape of the wave that is interesting the lower mass. And the idea is that here the wavelength is larger, and here the wavelength is smaller. All right. So I want to give you the possibility to have also an intuitive vision of the problems of the vibration. And it is difficult to be done right now, but is much more interesting than making thousands of calculations without understanding anything and finding out the numbers of the results. All right. So I wanted to give you the concept of the propagation velocity. As a consequence of the propagation velocity, and of the wavelength, the concept of the frequency, the concept of the period, and we are getting those concepts in the example that we made before. And here it is very important that we say frequency, velocity divided by wavelength. Frequency, velocity divided by wavelength. The frequency is the same in the two domains. It's exactly the same. And so if this one is smaller, this also is smaller. With respect of that, where the propagation velocity C2 is larger and the wavelength is larger. All right? So finally, if we're making the calculation, we are looking at a consequence like that. We will give you the MATLAB code that is doing this exercise. That is, in my opinion, is quite interesting. So you will play with the MATLAB code of that, and we are trying today to make a little bit of the theory that is the theory with which is written the MATLAB code, right? And working with the MATLAB code, you will change all the parameters and change the length, whatever, and then using also a force. So we are studying the free motion, and studying the free motion, we are writing the analytics equation that are able to calculate the shapes. And then we are in a procedure that is peculiar, that is exactly very similar to the procedure that we are using for the free motion. We are also adding the excitation force here. And we are adding an excitation force that is an harmonic force. The purpose of all of that will be to show that moving the frequency of the excitation, playing with the frequency of the excitation of this force, you will recognize with your code that is running that the shape of the deformed shape of this object, when we are approaching with the excitation frequency one of the natural frequencies of this system, when we are approaching we are moving the frequency of the excitation, and we know that this object will have modes of vibration, natural frequency. It's exactly the same if the mass is the same of left and right, is the cable that you studied the last time. Is exactly. And so it will be a little bit a variation of that with some a little bit more complicated because the mass per unit length has two domains, and so it is not exactly the same, quite similar. But you will recognize that moving this this frequency of excitation, approaching one of the natural frequencies, the shape of the vibration will copy exactly the shape of this specific mode of vibration having that frequency. And the amplitude are jumping up to infinity. Right? The purpose of this, all of that, is to play with this piece of code, recognizing that moving the frequency, you are jumping, you're getting into a situation where the amplitude are jumping up to infinity, and the shape is becoming equal to the shape of the specific mode of vibration that is being excited in resonance. All right? So this is the purpose, and so unfortunately, we must do the calculations instead of just speaking. That is very easy. All right. So we are using two domains. And we are writing that in the left domain, that is with running space coordinate x1, we are showing the transversal motion of the cable 1 that will be VW x1 time. Then we have a second domain that is starting from the back because it is useful for purposes of simplification of the calculations. And this domain is the domain number 2. And we will have the function W, function of x2 time, that is telling the story of the transversal movement of the cable on the right side. All right, well, it is the two objects are the two tensioned cables, so they are obliged to satisfy the partial differential equation, and so we are writing the two partial differential equations. All right, so we have two functions, W1, W2. They are satisfying the PD of the cable in this way. What is wrong in what is written here? What I forgot to say? I forgot to say that this is C1 and this is C2. So those two are different. All right. Well, so the solution will be the time function is the same. The time function is the same because the two bodies, the two domains are sharing one section. In that section, they are moving exactly the same, so the time function cannot be different. It must be equal. And so in order that those functions are satisfying the partial differential equation, we are using the separate variable approach. And so we are saying that the two functions are given by the product of the time function times the space function. in order to satisfy all of that, it must be that G two dots divided by G is equal to C1 second divided C Ho sbagliato. I think to use exactly the same formulation, the same symbology that you used with the Julia. So we write the partial differential equation, and we divide by G and phi this equation, and we divide by G and phi that equation, and so we are calculating G two dots divided by G equal to minus omega 0 square, in order that is not expanding, so we have this minus. But then, in order to write the space function, we have that here we have the propagation velocity square that is staying in together with the function of phi, the function of space, and so finally, if we are looking at the if you're looking to the function G two dots divided by G equal minus omega 0 square, from this we get this solution. All right. If we look at the second, that is C square, sorry, that is C square phi second divided by phi equal minus omega 0 square. We can write all of that like omega 0 square divided C square. To this quantity we give the name gamma, all right, gamma square. And so the function that we should write is sinus gamma x, all right? You were used to write sinus gamma x and cosinus gamma x. You wrote like that for the cable. All right, yes, but this gamma can be written as omega divided by propagation velocity, all right? And so we prefer in this situation to write everything like omega divided propagation velocity. And so we write, instead of writing the general solution of the left domain and the right domain as the harmonic space domain harmonic shape in sinus and cosinus of gamma x, gamma 1, x1, gamma 1, x1 here. Instead of writing a sinus and cosine of this, we prefer to write, instead of gamma, omega divided by c. It is exactly the same. So we are doing exactly the same story that we did yesterday, the Friday, but we write showing the frequency. All right? Is it clear? Oh, yes. Okay. Minus. Yes, thank you. All right, minus gamma 1. Yes. All right. Very well. So, so this is the explanation. I have to go a little bit speedy, otherwise we don't get to the end. All right. So for this reason, then we write for the second W2 x2 time equal and so we have two shapes that are different because this is gamma 1, this is gamma 2, and the time domain function that is exactly the same, because we said from the very beginning that they are sharing the same time function because they are connected. Well, so this is the starting point. Next, which are the boundary conditions that we have to impose in order to write the free motion? So the free motion comes from having imposed the boundary condition to the problem. So the boundary conditions are the null displacement at the two constraints. So we will write that the function W1 at the location 0, whatever is time must be equal to 0. Then we will write that for the domain 2, the function W2 at the location 0 is equal to 0. So the boundary condition is W1 0 time equal 0 forever time. W2 0 time equal 0, whatever is the time. Then the other condition is that W1 at the location L1 time is equal to W2 at the location L2 time. All right? So at the connection at x1 equal to L1, x2 equal to L2, W1 is equal to W2. All right? Then there is an equilibrium. All right, we positioned the coordinates like that. You will understand soon, using those two boundary conditions, that it gives a great advantage to use 0 down here. But because of they are reversed, when we are looking to the equilibrium of at the connection, and the equilibrium at the connection will say that here, where I have the infinitesimal length of the cable, where it gets the cable that is coming up from the left, and where we get also the other cable that is coming up from the right, the positive derivative of the cable is this one on the left, and is that one on the right. This is the positive derivative. So the growing, increasing derivative goes like that. The positive derivative is positioned like that here. The positive derivative, so dw2 dx2 larger than 0 that I must use in order to write the generic condition has this direction. And so if I have to write the boundary condition of the tension, that is, so this quantity here is tension 1 dw1 over dx calculated at L1, all right? And down, and this one will be T2 dW2 dx2 calculated at L2, all right? What is wrong? T1 is equal to T2, all right? We do not have different tension in the cable. The two domains are sharing exactly the same tension. And so this is tension, and this is tension, all right? And so I have to write that T dW1 dx1 plus T dW2 dx2 L2 L1 equals 0. Okay, so they are adding. So the total of that must be 0. Okay. The total, this saying that the total must be 0, it means that at the location where we have the connection, the derivative with which we are getting here from the left is exactly the same of derivative that we are getting out from the other one. All right. So this will be T1, and this will be T2. The two of them, they are adding, and this they must be 0. And so this derivative will be negative, and this derivative must be positive with respect to the convention that we used, dW1, dW2, x1 and x2. All right. Pay attention. So we must be consequent to the convention that we are using. Consequent, it means that it is useful for me to have this convention because there is a symmetry that we are recognizing now. But now, finally, in the boundary condition, then we have to use it correctly. Well, so we have a problem into 4 unknown, A1, B1, A2, B2. Those unknowns are defining the shape. And then there is another unknown, the natural frequency. So let's write the boundary condition. So here it is better written, but we are making comments. So first, so this is the W1 calculated at the location 0. That is A1 multiplied sinus omega divided C1 0 plus B1 cosinus omega divided C1 at 0 plus A2 that is must multiply 0 plus B2 multiplied 0. The same is the second boundary condition on the second W2. W2 at the location 0 is equal to 0, so 0, 0 multiplying A1 and B1 and A2 and B2 multiplying sinus at the location 0, cosinus at the location 0. The same displacement at the common boundary common connection. So omega 0 divided C1 L1, omega 0 divided C1 L1. This is the domain 1. Domain 1 multiplied A1 B1. Domain 2 A2 B2 multiplying sinus at the location L2. B2 cosinus at the location B2. Derivative, so the boundary connection of the this boundary connection here. So we must say that we must make the derivative. So the derivative is cosinus, but I have to multiply tension, so I have to say T dW over dx calculated L1, 1, 1, all right? So at the location L1 into W1, derivative with respect of x. Derivative with respect of x of this function here, what we get out from the harmonic function is omega 0 divided C1. All right, and so we should have T tension omega 0 divided C1. That is the same factor for everything, but for the second domain is omega 0 divided by C2. All right, the tension is equal everywhere, and so I have to remember that here I have the tension. All right, I write the tension down there just because for the further problem that we will do for the forcing, we must remember that this T. Here we can cancel. So here we can write omega 0 divided C2 sinus cosinus minus, this is minus sinus omega 0 divided C2 L2. All right, anyway, in the slide you have everything very well written. And so here is minus omega 0 divided by C2 sinus omega 0 C2 calculated at L2. All right, well, so what is interesting that we must that is very, very general is that the boundary condition that we write in all those problems are writing an homogeneous problem. So we are writing a matrix multiplying a vector of unknown that must be equal to 0. All right. But pay attention that in purpose, we decided to write, to make clear that here I have omega. I wrote omega, I didn't write gamma. I wanted to write omega, considering that gamma is equal to omega divided by C. So I want to show that this is omega. I want to show that this is omega in order to clearly understand that this matrix is parametrically dependent on the natural frequency omega 0 that is, let's say, a parameter that is an unknown parameter. And so all of that is H omega 0 matrix multiplying the vector of unknown constant equal to 0. So this is the generic way in which we are writing the boundary condition. An homogeneous problem, parametrically dependent on the natural frequency that is not defined, but that must be so that the determinant of this matrix is null, because we know that having the purpose of getting a solution of the homogeneous problem that is not trivial. Not trivial means that the solution 0, 0, 0, 0 is a perfect solution, all right? So whatever is this square matrix, the trivial solution 0, 0, 0, 0 is a solution of the problem, all right? But in order that the solution is not trivial, so we have a set of numbers here that are a solution, it is necessary that the determinant of this matrix is null. What does it mean that the determinant of this matrix is null? It means that the order of this matrix is not 4, but it is 3. So it means that one of the 4 equations that we are writing here is linearly dependent on the other. So when the determinant of this matrix is null, then it means that one of the 4 equations, here the rank, the number of equations is 4, but the rank of the problem must be 3. It means that one of the 4 is linearly dependent, is a linear combination of the other, and so that it happens, that in order to write the solution, when we have that the determinant of this is equal to 0, then we write the problem putting here 1, for example, in this location, and then here we write A2 divided A1, A3 divided A1, A4 divided A1. So we are writing a problem where the unknowns are becoming not the actual coefficient A1, 2, 3, 4, but the ratio of those with respect to one of them that usually is selected as the first, that is to which we are giving in purpose one symbolic number, for example, 1. And so we are writing the problem, positioning here 1, so that so the problem becomes those numbers that are given here that are translated down here, all right? So this one is multiplying those 4 coefficients, all right? All right. And so the problem that has a rank equal to 3 will be written with those 3 equations, multiplying those 3 unknowns, and so equal to a set of numbers here that are those numbers that are on the first column of the problem. I hope that you, in your life, you sometimes solved a homogeneous problem of a linear problem with a linear homogeneous problem with the matrix and reducing the order of the matrix after having selected that the determinant of the matrix itself is equal to 0. I hope. But so the physical understanding of the problem is that we are not looking at specific unique solution for those 4 numbers. The solution is a relative amplitude of the 3 with respect of the first. So we are not giving a specific solution, but we are giving a shape of the solution. And this concept that we are giving the shape of the solution is actually fully representative of what is the case into the vibrations. So the reason why the consequence of being those numbers determined unless the scale is that the shape, the model shape that we are finding out is defined unless the amplitude, all right? So we are giving a shape to the modes of vibration. We are not giving how much they are moving, okay? So we are just saying the shape, which is the shape of the mode of vibration. The shape of the mode of vibration is described by those ratios that with which we are writing the homogeneous problem. All right. So in case you do not have very clear the way in which we are solving the homogeneous problem, the matrix algebra of the matrix linear algebra, specifically for the homogeneous problem and then for the not homogeneous problem, you must go back and study the solution of the matrix algebra of the linear homogeneous problem. I don't go more in details than that. I give you an intuitive view and then the practical way of working, but it is necessary that you are going back to this little bit of mathematics. All right. Well, so the purpose of all of that is saying that we are searching for the condition null determinant. So finally, after having made this not very rigorous digression into the problem, into the linear algebra of the homogeneous problem, we say that at this point, the condition is determinant h omega 0 equal 0. So it must be determinant equal to 0 in order to have a not trivial solution. And so the way in which we are approaching those problems in order to write the free motion, the modal shapes, the solution of the free motion of a little bit more complicated problem with respect to the simple tensional cable, is to understand that now we have this very incredibly complicated problem to find out which are the numbers that inserted into the transcendental functions that are the trigonometric functions is making the miracle to give the determinant of the order 4 equal to 0. So you say that it is impossible to find an analytical solution to that. So you should recognize that it is incredibly complicated to find out which is the value of omega 0, because here the unknown, the free parameter is omega 0. Is the only free parameter. And so we have to search the value that is making null this determinant. So the solution can be only numerical. And from a practical point of view, all right, from a practical point of view, into the code, the matter of code that we are giving you, what is doing the code is calculating the magnitude of this determinant and is plotting. So we are following the numbers of the numerical calculation of that determinant. So we have all the values. So we have C1, C2, we have whatever, all right? So the idea is to show that approaching a specific value that will be omega 0, 1, the determinant goes down. And it will be 0. And then from here, it will jump up again. and this will be omega 0, 2. And so we will recognize that it's possible to find a numerable infinity of solution. Numerable, it means that it is an infinity that it can be associated to the natural numbers 1, 2, 3, 4, infinity. Okay. So it has the size of the infinity of the natural numbers. And that's it. And so numerically, we find out the values of omega 0, 0, 3, whatever, that are making null the determinant. We substitute those numbers, omega 1 into here. We know that this, in this condition, one of those equations is linearly dependent to the other. So we make 1, we give the value 1 to the first of those coefficients, and we solve the linear problem associated to the other that will be now the ratio of the second with the first, the third with the first, the fourth with the first. So the solution will be in terms of a set of numbers that will be defined unless the scaling quantity that was defined giving to the first. For example, the value of 1, all right? Of course, play with MATLAB. You just push the button and you ask for having the solution of the homogeneous problem. And it is very easy. You get it. The point that you understand what is happening is a different story. We will ask you for what is happening into the oral exam, for sure. So it is necessary that you are aware of what is happening when you push the button of the codes that are giving you the solution of the problems. And it is necessary that you understand that you have something that is not defined in terms of which is the amplitude, but it is defined just in terms of which is the shape. Then I made it very difficult in order to give the possibility to understand that if the problem has 10 degrees of freedom, has 10 boundary conditions, the complication of the problem grows, all right? But here, the problem is very, very simple because the sinus of 0 is 0, isn't it? Sinus of 0 is 0, and so this is null. Cosinus of 0 is 1, right? And so this is 1. Sinus of 0 is null, and cosinus of 0 is 1. And so what happens here? It happens that b1 multiplied by 1 is equal to 0, and so b1 is equal to 0. And so always in this problem, we have b1 equal b2 equal 0, okay? And so the rank of this problem is 2, and so the only part of the problem that is surviving is sinus b1 . Let me see if I did it correctly or not. I don't know. All right, it is like that. So if you play with the two equations and considering that B1 and B2 is equal to 0, this is the way in which it is written. Now the determinant equal 0 now can be written as one single function. So it is so the function sinus. So I don't write the function, it is written into here. So the determinant equal to 0 is sinus omega 0 divided C1 L1 multiplied 1 divided C2 cosinus omega 0 divided C2 L2 minus, or that is plus, so the product of those plus the product of those, because here is this minus sign, equal to 0. So you write a function that is a function of the trigonometric function where omega 0 is the unknown, that is much more simple than, so it is, and so the request to MATLAB is to find the value equal to 0 of that function of omega 0. That is extremely simple now. All right. All right, now, so you find, now, let's go to the end. Let's go to the end. So you write the problem, putting here 1, putting here A2 divided by A1, all right? And then you find out with the value of that specific number. So you get into here with omega 01 or omega 02. So with the numbers that are making the determinant null, you are putting those numbers into the second equation, for example, okay? And with those numbers, you are calculating which is I explained it in a very bad way, so I repeat what to do. I repeat. You select, for example, omega 0 first. You write omega 01 into here in all the locations, all right? So this quantity becomes a known quantity. Here you have 1. 1 is multiplying this quantity, and you bring this on in the second part at the other side of the equation. Now you have that A2 multiplied by this quantity is equal to this constant, and you write the value of A2 divided by 1. So you calculate the value of A2 divided by 1, A2 divided by A1, having substituted 1 into, and having substituted omega 01 into here, and having written 1 here, and having left one single equation where A2 divided by A1 is the unknown. And so next, what you will write the solution of the problem as W1 function of x1 time equal to 1 So we started with this generic solution. In this generic solution, we had A1, B1, and so we had the presence of sinusoidal, cosinusoidal. A2, B2, sinusoidal plus cosinusoidal. We use the boundary condition that whatever is time at the location 0 is null, so we cannot have the cosinusoidal solution, because the cosinusoidal solution at the location x equal to 0 is different than 0. And so this is cancelled, this is cancelled, okay? So using the two boundary condition at the location x equal to 0, and the purpose of having 0 here and the x2 in the opposite direction, and x at 0 here and x1 is into this direction is in order to suddenly reduce the order of the problem and cancel this cosinus and this cosinus. This is the purpose. If we are not using that, if you are making a boundary, a reference system x1 here and then the other one here, it is complicated. It becomes much more complicated, all right? And so the first two boundary conditions are canceling this and canceling that. At this point, we have the number omega 0 I that is giving null, that is making null the determinant with whatever one of those omega 0 I, so with the ith natural frequency, that is the ith parameter omega that is making null the determinant, we are entering the problem that is reduced in the order 2. It is homogeneous, so it is reduced to the order 1. We are putting the number 1 here, and we have just left one equation. This left one equation is the equation that is writing that this quantity multiplied by the unknown A2 divided by A1, that is the unknown of the problem now, is equal to what? To this quantity multiplied by 1 that is made down here in the second, in this position here. And so we write that with whatever omega 0 I, we have a ratio A2 divided by A1 that is index I, that is specific of the ith mode that we are looking at. And then we have a shape function that is sinusoidal function for the domain 1 that is made by the omega 0 specific of the ith mode that we are looking at divided by C1 multiplied by x1. So we are writing what we started with. And then is multiplied by the time domain function that is the cosinusoidal function with a generic phase phi that is running at the natural frequency omega 0 I. That is actually is the natural frequency that we found for being one of the natural frequencies. For the second domain, we have to write, we wrote 1 here, because we wrote A1 equal to 1. And for the second, we are writing the relative amplitude of the second with respect to the first. So we do not know which is the actual amplitude. We have the generic amplitude of the free motion, and then the specific value of the free motion will be given by the initial condition. We are given an initial condition, and we will find out which is the scale of the problem that is running. In order to write that the scale of the problem is free, we write the number 1 here, the number A2 divided by A1 that is given by the solution of the linear problem with the position of having reduced the rank of the problem. All right? And so this A2 divided by 1 is a number now. It's becoming a number. And so for the ith mode, here we have a number. For the third mode, we have another number. For the 50 mode, we have another number. So the relative amplitude of this quantity with respect to that quantity is described by the solution of the homogeneous problem. 1 second, I finish. And then I must say that there is a scale that is free. The scale that is free is another constant here that is exactly the same, that is saying larger, smaller. So I can have the same shape, large amplitude, small amplitude. this quantity will be given by the initial condition. And then at which frequency are running those two domains? With the equal frequency omega 0 I, that is the same because we have one mode, we have the mode of vibration 1. For example, this object that is shown here, in my opinion, this will be the second. This will be the second. For example, here we are showing the second mode, for example. I don't know exactly because, but we have the shape that is given by the domain 1 with a wavelength that is smaller with respect to the shape that is given to the domain 2 with a wavelength that is larger for what we said at the very beginning. And then they are oscillating with the frequency that is the omega 0 I that is specified, omega 0 for the first mode, omega 0 that it was the solution of the null determinant problem. Null determinant problem that is very clear now. It is a function. It is a function of omega 0 that must be equal to 0. And the MATLAB code is telling you which is this number. And then the initial condition are saying which is the amplitude of this component, because then what we'll have is that we will have that the different modes could be excited in a different way. Okay? And so we could have that the one mode has a very large amplitude, another mode has a smaller amplitude. And so we have that there is a coefficient that is moved by the initial condition that is telling how much. So there was a question? The AI, so this object here. So I think that you are a bit confused that a new constant is getting into here. All right? Is this the problem? Yes, but I mean that in a very practical way, I have to find a way of representing the concept. The concept is that the homogeneous problem is not telling me which is exactly this amplitude. It cannot tell me which is exactly. It can just tell me which is the relative amplitude of the second with respect of the first, of the third with respect of the first, of the generic one with respect of the one that we selected to be the reference. All right? To be convinced about that, we should be, let's say, very confident in the solution of the homogeneous problem. So this thing that is a bit confusing shouldn't be confusing, because we should have in our mind that the homogeneous problem cannot give us a precise solution. It can give the shape of the solution. It gives a very precise solution, but just in terms of which is the shape of the solution, not which is the amplitude. All right? We must be convinced about that. So the way to be convinced about that is to play with the numbers. You have to play with the numbers. You have to build yourself an homogeneous problem, and to play with the numbers, showing that if a set of numbers are the solution of the homogeneous problem, this set of numbers multiplied by 2, 3, 4 is continuing to be the solution of the homogeneous problem, because you have a problem where you have a matrix, a vector equal to 0. If this vector is multiplied by 100,000, it is still the solution, because 100,000 multiplied by this quantity makes, if this quantity is making 0, if you multiply by 100,000, it makes 0 again, right? If you are scaling this, multiplying by one number, this number is multiplying also 0. So if you are scaling this by 1,000,000, 10 to the 6th, 0, 10 to the 6th, is satisfied. This 10 to the 6 is multiplying the vector, and so the same numbers multiplied 10 to the 6 still are the solution. And so this is the same of saying that I am positioning one here, fixing not the absolute amplitude, but the scaling of one with respect of the other. So it is not, we are not obliged to position here 1. I could position here 2, whatever number, and then the other number will be scaled by 2. So you must be aware that the homogeneous problem is giving me the shape of the solution, not the actual value. The actual value is the initial condition that is telling me I'm starting with a large amplitude or with a small amplitude. In order to say that, it is necessary in any case that with the mathematics we are writing some numbers, and so I have to write in some way that the scale of this with respect of that has a number. And so the best way to do it is that one of those is 1 and the other are something with respect to 1. And so if they are larger, we understand they are larger. And if they are smaller, we understand they are smaller. So if they are less than 1, they are smaller than this, that is the reference. That's it. At this point, as the amplitude must be free, I have to write that they are free. And so I have to position another constant that is the same in the two domains, exactly the same, that is a constant depending on the mode. I have to say that that mode is modulated by another constant that is saying becomes larger, becomes small. So if this constant is telling us which is the size, then with the specific solution, with the specific eigenvalue, so natural frequency omega 0I, it is oscillating with the frequency omega 0I. So this is cosinus omega 0I. And then here, then the free motion is dependent on a scale, that is the size, the amplitude at which is excited that specific mode, and then there is also, we can have a phase, okay? The amplitude and the phase is well represented by the representation in the complex domain when you have a constant where this constant could be a complex number, and let's say that all of that becomes extremely simple if here we write C1 So if this is a complex number, and this complex number is this is the rotating vector e to the power I omega 0 it, right? So this is the rotating vector. This is the complex number C1 having the phase phi, and this is finished. So we are just saying that the solution is oscillatory with the frequency omega 0I with a phase and an amplitude just using here CI, sorry. I have to say CI. Coefficient, complex coefficient CI that is giving the magnitude and that is giving the phase to the rotating unity amplitude vector that is telling which is the frequency. So the best way of writing, of course, is using the complex notation, and all of that, the phase and the amplitude is just the complex vector that is saying how it starts, okay? And then it will go ahead to be being equal. But the different modes could start with a different phases for some reasons. All right. I tell you just one extra concept. The boundary condition with which we wrote the equations were, let's write it then here. The last boundary condition was tension derivative, tangent, okay, tension dw over dx1, 1, all right? And we said that this component plus this component is equal to 0, all right? We wrote the equilibrium at the connection. Now, if we are pushing here with F0 sinusoidal, we will just say that this plus that is not equal 0, is equal to the harmonic force. And so, in order to write the problem in this forced problem, we write the forced problem as a boundary condition. The excitation force is becoming a boundary condition, is the boundary condition of the equilibrium at the connection. And so the fourth equation becomes T dw over dx1 at the location L1 plus T dw2 1 at respect of x2 at the location L2 equal F0 is finished. So the same problem that we wrote for the free motion becomes exactly the same mathematics of the forced problem where the force is becoming a boundary condition. And the matrix will be exactly the same. So here we will have sinus that will be 0. Then we will have the second. The second will be B1 will multiply 0. The second is cosinus omega divided C1 multiplying 0 and so on. All right? So we write into the matrix exactly the same mathematics, exactly, but the frequency will be the excitation frequency. So we say that when we are exciting with a frequency that is a specific omega, the system is answering exactly with the same omega. So we are putting this condition. Let's say that in order to make it, to say it correctly in a formal way, This is true only when any other excitation coming from the initial condition has been cancelled. So in order to say that I am getting into with the excitation omega, the solution of the problem is a motion at that frequency and that's it. It is true if the memory of the initial condition that are exciting all the modes, that are running all of them at a different frequency, has been cancelled because those modes were damped by the intrinsic damping of the system. So in case we are working into the ideal world of null damping, whatever is the initial condition, it stays infinity. But in the real world, everything is dying. Also the vibrations, because there is damping. And so the memory of the initial condition that is the vibration of the system, each mode at its own frequency is disappearing. And if I have an excitation at that frequency, after a certain time, it is the only thing that is surviving. So the only surviving things is the answer, so the response of the system at that frequency. And so we will write the problem putting into here, into this mathematics, omega equal to the frequency of the excitation, and the problem becomes a linear problem with a known vector on the right side. And there is another small detail into the calculation. The other small detail into the calculation is that we cannot cancel the dependence on the tension. In the last equation, we have tension here. This tension must, so in the homogeneous problem, the tension is cancelled because it's equal to 0, and so we are discarding. So we are dividing the right side by t. Look, please, you will do the mathematics. Doing the mathematics, this tension here, that is and the omega that is coming out from the derivative with respect of x, that is getting out omega 0. So those constants that were cancelled in the free motion, because in the other side of the problem there was 0, they cannot be cancelled. And so here there is a t omega 0 that was cancelled in the homogeneous problem cannot be cancelled. So the last equation, we must keep an eye on the last equation because we are not dividing by t, because here we have f0, all right? There is the other fundamental comment that is left, you will find into the discussion of the slides. I suggest you that we give you the code. We give you the code, and you run the code and you play with the code. This is the best way to learn. So you play with the code, but you must go into the code, understanding how it is written, changing the parameters, and looking at the shapes and working with the code. You will learn much more than listening to a lot of theory. All right? So you have something from what we said today. You have an idea. Then you must go into the numbers. You must go into the numbers. Into the slides, everything is written with all the details of the theory that are needed. And then there is also the piece of code that we are making you available very soon. I ask Julia that and then we suggest to play with the code, and that is interesting, really. All right, we stop here.